Welcome to this demonstration of Flotherm XT across the design flow. What I'm doing at this point is I'm working on a conceptual design for a board for a wall-mounted network system. So I'm adding devices at this point, simple representations of components, and we're assigning appropriate materials and power information. We also need to give the device an appropriate size and locate it using the graphics display area controls available within the software. So this is a representation for the main chip, and it's positioned on the top surface of the board. We can do similar things, or we can use our parts library to create other devices. Now what I have is a previous design of a pin grid array which I'm interested in, and I drag it across and position it in place using the controls to the left hand side of the main chip. We do the same operations for the rest of the thermally significant devices on this particular board, and we also add in a connector block at the bottom. We need an enclosure for this, so we go to our smart parts library and we create an enclosure smart part, call it housing. It comes in with a certain size, it comes in with a certain thickness. We can adjust these. We add a material for this enclosure, and we then locate it in space using the GDA controls and two or more different views within the application. At this point, I'm ready to do an analysis. It's a conceptual design of a sealed system in free space. We add in a solution domain of a certain size, and we click on Solve. The software automatically meshes the system, and we can see the solution progress on screen here, which shows the convergence within the software. We can then look at the results using cut planes, looking at both the flow field and the temperature distribution. We can also take a closer look at the board by plotting surface temperatures on the board and the components. And using the plot probe, we can make an assessment of just how hot the devices are. Now clearly the main chip is a problem. That component is too hot, and we need to consider modifying this design. Now this will include adding holes to the enclosure smart part, and it could also include adding a heatsink. Now you can see a very simple plate fin heatsink here, created using a smart part technology. It's mated and located as appropriate onto the main chip. And for the housing, we modify the existing design, and we add the holes to the bottom of the enclosure and to the top surface. We're now ready to click and solve again. This time we're going to take a closer look at the flow distribution in order to understand the cooling behavior of this system overall. So the airflow comes in through the bottom row of holes. It passes across the surface of the board, and you can see the airflow through the heatsink. There's some recirculation within the system, but then the airflow leaves through the top set of holes. We can also check the temperatures again, and this time we have compliance. We're happy with this conceptual design. Now at this stage we've moved on, and we now have an appropriate design available for that board from our EDA software. So this is looking at Expedition Enterprise, and I'm showing you a particular board layout. What we do is we export this design out and import it into our Flow EDA Bridge module. Now this application allows us to do a number of things. We can filter out thermally irrelevant components in a number of different ways, and we can also, as shown here, replace the simple representations of components with selected thermal models from our library. Now these could be 2-resistor, they could be detailed, or they could be multi-resistor representations. We have a combination which are used in this example. Once we've done this, that's completed that step, we can also import power information through a CSV file. We're ready now to transfer all of this to Flotherm XT. And inside the software, what you will see is a full 3D representation of the PCB and the devices on the surface. At this stage, we locate the connector for the new board geometry. We suppress the original simple design. And we also have to do a bit more work in this, but before doing so, let's take a look at one of the models which are actually originated in Flotherm PAC. And it's showing you there the internal structure, including the lead frame, the bond wires, all the way down to the die. Other devices are simple or 2-resistor, or some of them still have leads or the pins represented. We're going to now evolve the enclosure design and also consider the heatsink. So we're going to bring in a more rounded, more aesthetically pleasing design of the enclosure. And you can see it's got a curved front face. We've also modified the vent geometry a little bit. Just adjusted it slightly, and we're also going to revise the heatsink. Now all we do here is keep it as plate fin, but simply add a bit of curvature to the ends of the fins to make it fit more easily into the shape of the enclosure. We can also see at the back of this the mounting holes which have been added. We're now going to solve this in its real environment. So we also need to add in a representation for the wall. So it's a very simple cuboid representation, but the system is now truly wall mounted. We're ready to click and solve again. And we can take a look, once that's complete, at the new results. So I'm looking here at the temperatures, and I can confirm that the component, the main chip, is not too hot. We're looking in detail now at the detailed device all the way down to the die, and that component is also compliant now. We're looking now at the flow field, and we're looking at the cooling performance, and it's acceptable. And we may at this point want to take this information in a form appropriate for a design review. So we can use the report generation function within the software. We can take screenshots, and we can export this out as PDF, as HTML, or as docx format. Within this report, you'll see a table showing the device temperatures, and it will flag the ones very effectively in terms of how close they are to the maximum allowable temperatures. And at this point, the detailed design is complete. Thank you.